University. We'll be talking on primitive cycle decompositions of Kn and Kn minus I.
Thank you. Thank you to all of the people who have made it possible to come here and give this talk. Thank you to all of you guys for coming to listen. So this is joint work that I did with my advisor, Dr. Michael Schroeder, as well as with Chandra Dinavaki and John Asplin. And from at the beginning of when I started this research, it was funded by the NASA Space Research Grant. So that was wonderful as well. So let's start with a couple of basic definitions that you most likely already know. So a graph is a set of vertices and edges, and a decomposition of a graph is a partition of the edge set. So for example, here we have a graph on 6 vertices. Did not capture it. Hello? Okay. And so like that? Yeah, okay. All right. I can move things now? That's nice. Okay, so a graph, as you may know, is a set of vertices and edges. Here we have an example of a graph on 6 vertices, and a decomposition of a graph is just a partition of the edge set. And so here we have decomposed this graph on 6 vertices into 5 different parts. You have the black part here, the blue part, the yellow part, the green part, and the red part. So now that we have a graph decomposition, let's play a little game. So we start with our graph decomposition, any that we've chosen, and we pick an initial color to infect. And then the infection spreads by the rules that are shown on the slide. So if an edge is infected, its endpoints become infected as well. If the endpoints of an edge are infected, then the edge itself between those 2 endpoints are infected. And if an edge of one color is infected, then all of the edges of that color become infected. And so when you let it proceed this way with these rules, the question is, well, do we end up infecting the whole graph, or do we just infect a smaller part of the graph? And the goal, the real idea is, does the choice of the first color you decide to infect really matter? And so here we have an example from the first slide of decomposition. And let's go ahead and decide that we should probably go ahead and start by infecting the red. And so I'm going to show that it's infected just by having it bold in color. And so after we've infected the red, we see that this vertex and this vertex have been infected because of the rules that if the edges that are infected touch that vertex, then they are also infected. And then also, the edge connecting the 2 must be infected, and that's a green edge, so all of the green edges must also be infected. So now these are the parts of the graph decomposition that we have infected. Well, now that we've got all of these other vertices, we've got every single possible vertex, and so all the vertices of the graph are infected, and therefore we have that the entire graph, all of the edges and everything, is also infected. And so with that, we see that if we choose the red part, then we end up infecting the entire graph, and we win in a way. But if we start with the black part of the decomposition, for example, we see that we would have to have this edge because it is connected by 2 vertices that are infected. And so with that, we know that we have the blue cycle, or the blue part of the decomposition, which here is just one line. And then also we would have to have this edge because we know that 0 and 2 are infected. However, now that we have that, those are the only edges between those four vertices, and so nothing else in the graph is infected. So by choosing the red one, we infected the entire graph, but since we chose the initial infection point as the black part of the decomposition, we have a smaller portion of the graph infected, but not the entire graph, and we cannot continue. So if we have a more positive example like this, we go through and we say, okay, well, let's assume that the yellow part is infected. Well, due to the fact that these two vertices were infected, we know that we have this black edge, and so we have all of the black edges that are infected. And now we know that since we have these two vertices, we have to have the blue edges also infected. And now with that, we have all of the vertices infected, and we have the entire graph infected. Now, if we start with the blue part, we have that these two vertices were infected, and so we have to have that the green part is infected because it contains an edge between those two vertices. And then with that, we also have that the red is infected because with the blue and the green, we have that 4 and 2 were infected, and red contains an edge between those two vertices, and so red also becomes infected. Well, with that, we have the entire graph once again infected. And so we go through this in this way so that we have green and we have red because of those, and then we have yellow, and we continue until we keep getting all of the vertices. And so we can do the same thing starting with red, we end up with the yellow, we end up with the blue, and we've got all the vertices, so all of the entire graph, all of the vertices and the edges are infected. Next, we can also start with the last part that we haven't tried yet, the black one. And so we have the red one with that. We have the yellow one as well because of these two vertices that are being used. And lastly, we have the blue part that is also infected. And then with that, we have all of the vertices, and so everything in the graph is infected. So in this situation, it doesn't matter which part that you choose as your initial infection, because either any of the choices you make, you end up infecting the entire graph. And so with that, we say that if the infection does fail and we end up with a smaller portion of the graph infected and know where to go from there, that the decomposition C has a sub-decomposition. And so for example here, we had the, this is the example from before that I showed you where we found that this was a problem whenever we decided to start with the black one. And so this would be the sub-decomposition of this decomposition. And then somewhat trivially as well, had we have started with the blue or the yellow, we wouldn't be able to go anywhere from there either, because with that we only have that one edge. And so this is, yet again, somewhat trivially a sub-decomposition of that graph as well. And so if we don't fail, then we say that C is primitive. And we thought a lot about the wording. We thought of non-decomposable, several ideas, but we decided on primitive. And so the example that we had before, where we went through each of the different parts and taking each of them individually and seeing where it leads, so that we would not fail each way, no matter which one we chose, we end up infecting the entire graph. We say that this is primitive. So this decomposition of this graph is primitive. So primitive decompositions have been studied for quite a while. In 1969, Joanne studied triple systems, which is just decomposing a graph into triangles. And actually, a triple, like the triples on their own, the triangle decompositions, they're technically a subsystem because they are an induced graph on those three vertices. And so because they are an induced graph on those three vertices, they just focused on guaranteeing that there were no other sub-decompositions, kind of ignoring the fact that a triangle itself is a sub-decomposition, or else every single triangle that they had, every part that they had would be a sub-decomposition on its own. In 1982, Mendelssohn and Phelps showed the existence of primitive K4 decompositions, so they took a graph and they decomposed it into smaller graphs of K4, and yet again, not paying attention to the fact that K4 is on its own sub-decomposition of the larger graph. Roger and Spicer in 1999 showed the existence of a primitive K4 minus edge decomposition. And lastly, Dinovaki and Roger in 2012 showed the existence of primitive path decompositions with each path having the same length. So we worked on cycle decompositions in specific where each cycle had the same length. And so we found primitive cycle decompositions of Kn and Kn minus a 1 factor depending on the parity of n into the cycles of fixed length. So here's an example of a complete graph on 9 vertices. Yeah. And this is actually the decomposition that we used. We decomposed it into 4 cycles. So each cycle has exactly 4 edges. And actually, this is a primitive decomposition. The way we did it, we created the decomposition in a cyclic manner. So we started by creating this cycle, and then as you can see, we just shifted over 1 so that the 0 goes to the 1, the 1 goes to the 2, and we just shift it over each time to go through and get the rest of the decomposition. And because of the way we did this, see for example, this one, if we infected this red cycle, we would know that 1 and 3 would be infected, and so the edge between them would be over here. And then with that, you have 8 and 1, and you'd be able to hop over here, and because of the way it's formed, or the way you decomposed it, either way, no matter which one you start with, you end up infecting the entire graph, and so the decomposition we say is primitive. Well, the first question we had, well, when does Kn or Kn minus the 1 factor even have a cycle decomposition in the first place? Well, this has been studied, and the main necessary condition is admissibility. I've got it written up here, but really all it means is that the number of edges in each cycle divides evenly into the number of edges in the original graph, so that you can actually divide the edges into cycles number-wise. And so both cases of Kn and Kn minus 1 factor were shown. When n is odd, the existence of n-cycle decompositions for Kn was shown by Hoffman, Lindner, and Roger in 1998, as well as Roger on his own in 1991. And an analogous question for Kn minus 1 factor when n is even was shown by Allspath and Gavlis in 2001, as well as Sonia in 2002. And so we worked on showing the existence of primitive cycle systems of both Kn and Kn minus 1 factor. And so we showed the inductive step for these. The base case hasn't been proven yet, but if it is true, then we've shown this. And so we've got it shown the existence of cycle systems for both Kn and Kn minus 1 factor, depending on the parity of n. When we were showing this, one thing we used quite heavily in our proofs was this lemma. And it's got a little bit of technical terms in it. Not really technical terms, a lot of letters. And so I've also got an example to show after this to help explain it. But basically, it's just to let G have a decomposition. So we have a decomposition, and within that, a primitive decomposition, so a sub-decomposition within it. And we augment 2 parts of the sub-decomposition with parts from the rest of the decomposition, and then we replace the original parts with the augmented parts where we swap some edges, and then with that, we assume that if there is a sub-decomposition, that if one of the augmented cycles is in, then the other one is, and vice versa. And if that is the case, then we have that all of the vertices of the original sub-decomposition from the entire graph are used by the subsystem. So it's a little wordy. And so here we have an example that I worked on, actually. This is a graph of K17, I believe. And we decomposed it into 2 different graphs of K9. So this is a complete graph on 9 vertices. And we have a primitive decomposition of that, as I showed earlier, the cyclic one that I showed. And so we have that here, as well as another copy on the bottom. And then we have the bipartite between all of these separate edges. And we're 4 cycles, as I mentioned. And the way we decompose this part into 4 cycles is we just take the different pairs of the vertices, both on the top and bottom, and then we pair up the pairs of vertices, and we just stick in the complete bipartite graph between the 2 vertices. So for example, this would be a 4 cycle in decomposition, and we know for a fact that this would also be guaranteed to be a cycle in the decomposition. Well, because we have such a good, we have a lot of leverage on the way that we are able to label the vertices in the decomposition of K9 on both the top and the bottom here. And so we make sure that this is a part or a cycle in the decomposition up there, and so that we can do it this the way we would like to do it. And so then we pick our edges that we're going to be swapping to try and get rid of, disrupt this subsystem that we have here. And so we go through, pick the edges, we go through and we swap them next. And then, as the one that said, in order to conclude that all of these vertices are included in the decomposition, that if one of our augmented, either the red or the black cycles are in the subsystem, then the other one is as well. And so we have to go both ways. So we start out saying, well, assume that there's a subdecomposition and assume that the red cycle is contained within it. Well, in that case, we have to have the green cycle that is right next to it, because we have this vertex being infected as well as this vertex being infected, so they're both contained in the cycle decomposition, and therefore this one would also be contained. So we have the green cycle, and then after that we use all 8 of the vertices. Yeah, it's 8. And so we know that for a fact that we would also have to have this black cycle as well. So now we've shown that if we have the red cycle, then we have the black cycle, but now we have to go the other way around in order to show that we have all the vertices. And so here we have the black cycle being contained in the subsystem. And so we know that we're going to have the green cycle once again because of this edge right here this time, because those 2 are infected, and so we have to have the edge between them in the subsystem. And then because we are using all of the vertices here, we know that we would also have to have the red cycle contained as well. So now that we've done that, we know that if we have a subsystem, that all of these the vertices would have to be contained in it, as well as all of the edges connected. Well, after we've done that, we can actually kind of flip-flop our cycles, because we have an identical graph of K9 down here, so we can make sure that we label these in a way that we get this cycle, and then we know that these are going to be cycles in the bipartite graph between them. And so we have the exact same argument where we augment the black and the red cycles, and then show that if we have the red cycle, then we have the black cycle, and vice versa. So it is the exact same argument, only to show that we also have these vertices contained in any subsystem. Well, now if we have a subsystem, we know for 100% fact that we have these vertices as well as these vertices. So that's all of the vertices in the entire graph. So it shows that the subsystem itself would not be proper and therefore would not count. Some future work that comes out of this, the base case is still open. We've not looked into that yet. And then other graph decompositions, such as decomposing graphs into stars, larger graphs of KR, which is much more difficult than stars and other shapes like that, and other things like that. So those are some ideas that we could go from here, but we're working on this.